Good morning, or whatever time it is where you are as you watch this. So this is a build video for the CANEther, a somewhat more advanced module than the CANMIO, which I built previously. Although the build isn't much more complex, with one little exception, which actually doesn't need to frighten you too much, and I'll show you that as we get to it, as it's the first thing we do. CANEther is a very useful module. It allows you to connect your C-bus to your computer via Ethernet, and the effective way to use it is generally to connect the CANEther actually to your house network, either with a Wi-Fi extender or directly with a cable to your router, depending on how that's convenient. And that means that any computer or computers connected to your house network can now connect wired or wirelessly to the layout without them having to be directly connected to a module on the C-bus. I find that a good way to work. And if it's being used standalone, you can either just plug straight into the CANEther from the computer. Alternatively, you can plug in a little pocket router onto the CANEther and have a dedicated wireless network just for the layout. So that's how the CANEther can be used. So not currently available from the Merck Kit Locker. Hopefully one day it might eventually make it there. So you can get it as a bag of components from RME, or you can just buy a PCB and source your own components if you prefer. Build, my normal procedure is just to tip all the bits out of the bag. And take the circuit board to work on my workspace with a pile of components just over to my left there. So let's take a quick look at the PCB itself. So we've got the standard C-bus connection and driver chip on the left. We've got the PIC here, an Ethernet chip here, Ethernet management chip, and then the Ethernet connection, the RJ45 connection at the far end, and various other components in between. As with all my boards, it's the same form factor with exactly the same fixing holes. The outer set is for fixing the module. And then if you want to stack modules, such as using daughter boards with CANMIO, but also you might perhaps take a CANEther and stack it with a command station, maybe in a box, if you're making a central module for your layout. So the second set of inner holes can be used for standoffs to stack another board above the one we're looking at. Now, one thing on this one, if we look on the back, you will go, oh no, there's a tiny little surface mount chip just there, which is the first thing we'll do. Now, that's the MAC chip. Now, every Ethernet device in the world has a unique MAC address. And as a manufacturer, if you want to be able to put MAC addresses into your products, you have to spend out a very large sum of money and you get allocated a huge, great block of MAC addresses. Now, Microchip have done that because they have lots of devices that have MAC addresses built in, and you can buy this little chip, which is basically an EEPROM that has a unique MAC address programmed into it. So you only have to buy one chip from Microchip instead of spending out a large amount of money on them all. And that chip gives this module a unique MAC address. It has to be surface mount because that particular chip is only available in the surface mount format. However, your CANEther will work if you choose to wimp out and not fit the surface mount chip, or if you make a mess of it, because it will just use a default MAC address, which won't necessarily be unique. But since you're using it on your local network behind the router, it's not directly visible on the internet. And if you only have one CANEther, which is most likely, then it won't actually matter that your MAC address is the same as the other members' MAC address, perhaps, who also has a CANEther on his local network. So it won't actually matter if your MAC address is the same as another user's MAC address of a CANEther that may well have one of these on his or her network behind their router, because the two can't see each other directly. So I'm going to start with the surface mount assembly of that. Now, it's a good idea. Actually, it's a good idea anyway, but even more of a good idea when you're doing surface mount, just to give the board a clean over first. So a little bit of my cleaning solvent and my trusty toothbrush. Just give that a clean, and that gets anything from the manufacturer of the PCB, or if it's been lying around a bit, cleans all the pads off. Using them with these solvents, of course, in a well-ventilated area. Now for this surface mount work, I'm going to use a very fine tipped soldering iron tip. As you can see, that's quite small, and that's going to allow me just to get in and tap the individual corners to solder that device on. So my soldering iron has removable tips. Checking that it's cooled down enough. It's still slightly warm, so I'm going to use my pliers to take the end off. So on these Weller soldering irons, that just comes off. The bit comes out. And on the end of the bit, there is a number. This is a 7. And you can look up and see what temperature that corresponds to. The thermocouple inside is adjusted for the temperature, and the number stamped on the end. Number 7 for all normal use, leaded or unleaded. So I'm just going to put my soldering iron back together and use this very fine tip for the surface mount. Now, what you can do with is to have the PCB just either with a bit of blue tack or whatever. I seem to have got a little bit of solvent on the back, which is acting as a very good glue. There's a bit of super glue left lying around on the layout to make sure I can get that off again afterwards. But yeah, it's coming off okay. I will have to clean the other side. Do you want it rigid? Sometimes you can put it on a block of wood if you're doing a lot of soldering iron, and then you can move the whole thing around and orientate it. We're only doing this one little chip, so it's not too bad. So in your bag of bits, you will find a little bag with the surface mount component in. It's so small it's in a separate bag so you don't lose it. And there we are, one tiny little chip. So being careful not to spill it on the floor. I tend to use a pair of tweezers on here and just very carefully peel back the foil on here. You can, the other alternative is to push the chip through from the back. There's a tiny little hole there that you can just push through, and there it is. So having a close look at that, you turn the right way up. And generally speaking, you're probably going to want to use magnification for this bit. I'm using my Optivisor. And I'm just going to bring this right up close to my eyes so I can see it. And there is a little dot on the chip. Now I'm going to bring it up to closer to this camera. Now, with any luck, you might be able to see there's a little dot on that chip. Just about make out there's a little dot on that. And with magnification, you can see that with the naked eye without too much difficulty. Now on the PCB itself, there is a little dot. It is quite tiny, but it's just down this corner. So that is pin 1, and the dot on there needs to align with the dot on the circuit board. So there are lots of different methods for doing surface mount soldering, and different methods suit different people. I think the only person who's wrong is the one who says you must do it my way. So you can use solder paste, you can use hot air guns. For a single chip soldering like this, I'm just going to use the rework flux jelly, which you can get from the likes of RS or Farnell. Try and keep it off your fingers. It's not the greatest stuff in the world. Together with some very fine solder. So having cleaned the PCB, what I'm going to do is just take a little bit on the end of a cocktail stick. I don't need a big pool of it because I'm only doing one here. And then I'm just going to splodge some all over the pins on the PCB that I need to solder. Can then go away for the moment. And I've got this quite fine. This is 0.3 millimeters. I think the fine surface mount solder, which just makes it easier to work with on something as fine as this. So what I'm going to do now is just position the chip where it's got to go. And of course, it insists on trying to be upside down all the time. There we are. I think I've got it the right way up now. With my magnification, check where that dot is. Check I've got it the right way around. And position it more or less in position there. Now, for me, I find it easier to do it from the side like that. I can then come in with tweezers like that and hold it. You may hold it with a cocktail stick, tweezers. There's also specialist tools. There's all sorts of different ways of doing that. Now, because we've got flux already on the joint, what that means is that it's okay to bring the solder to the joint on the iron, which is not the way you would normally do it with through a hole or whatever. So I'm just tinning my soldering iron here, and then we'll grab a little blob of solder. And initially, I want to just tack the corners. So I'm going to hold that in place as central as I can. Tack the corner pin. I'm going to turn the board round. Put it steady with the device. So now both corners are tacked in place. I can just go in a more conventional way with the solder. Again, I'm using my magnification, as you can see. And so this one isn't the finest of pitches as soldering surface mount devices go. So it is amenable to just sort of soldering each pin in the conventional way, and there are only 6 of them after all on this one. So, and then I'm going to use a close-up visual inspection. So I'm going to come up right up close with the extra that I've got on here and have a look and see if they all look nicely soldered. One of them doesn't look great, the others look okay. So I'm just going to touch the iron back on that one that wasn't so good. So a little bit more flux on there. What you can do, and if I was doing a bigger, more complex, I would certainly do, is after tacking those first 2 on, is I would put another layer of flux over the top over everything, just to make sure it's all going to solder up together properly. So here I'm just going to remake that one I wasn't totally happy with. Hopefully that will now be better. So back up with the close up. Yeah, that's looking much better. So the joints are all looking nice. If you want, you could take your meter and check the pins are connected out to the right place of other tracks, but for me that's probably takes too long. And also, of course, in that close-up visual inspection, you make sure you haven't bridged any of the pins together. You need to go in with a braid if you have and get them apart. So there we have it. I can do a little clean up to make my surface mount soldering nicer. And there we go. That's the surface mount device soldered on. So that was the tricky bit. The rest is all standard through-hole assembly. So I'll turn my soldering iron to cool down so that I can change my bit to my normal one whilst I proceed with the next part. So as I did with the CANEther, I shall use my bendy jig, and I shall pre-bend all the resistors, diodes to the right size, ready for use. At this stage, I don't even worry what value they are or anything like that. That's to come. Should do the diodes as well. The diodes will be on a slightly, just the way I happen to lay out my PCBs, the diodes are on a slightly narrower. I think there's only the one diode in this one. Now, because there was some sort of residue on my work surface there, which was quite nice because it held the PCB a little bit sticky in place so it didn't skip all over the place while I was doing the surface mount. But of course, I kind of need to clean that off now. I'm going to be soldering stuff. We've already cleaned the back. Really good. So we'll now start putting the resistors in, and as always, I'll endeavour to put them the right way around. I'm familiar with the colour codes. If you're not, you can Google resistor colour codes and download a chart so you can check which resistor is which. And because I've labelled all the resistors on the PCB with their value in the centre as an assembly aid, although you can't see them once assembled, but that means that you don't have to keep referring back to the schematic now, or the parts list. You just need to refer to the value in the middle of the resistor there as to which one goes where. So over here, let's grab the diode. Haven't actually been that in tight enough, I think so. It's the tags on the end, which we'll get rid of. Because of the narrow spacing, I generally find that I just need to pull the diode in using the pliers. It's sitting there nicely now. Having made sure I've got it the right way around, and that the stripe on the diode matches the direction of the arrow underneath. So matching resistors values to what's on the circuit board. And putting them all the same way around so they look nice and so I can read them left to right. You don't have to do that, but I like to. Just as a note, the resistors for the LEDs are a slightly lower value than on most of the other C-bus modules. They're 1K instead of 1K8, and that's because this board runs at 3.3 volts because the Ethernet interface chip is a 3.3 volt chip, and therefore the lower voltage means we need slightly lower resistor value resistors on the LEDs to get the same brightness. Now these resistors are a slightly unusual value. If you work out the color codes, it's 49.9 ohms. They're specially for Ethernet interfaces, I guess, plus the 0.1 ohms going through the mag jab. They're creating the 50 ohms impedance that's required for the Ethernet interface. There are 4 of those, and they have to be 1% accurate. They're the ones with the 4 stripes on them instead of 3. And the brown stripe at the end instead of the normal gold stripe. The gold stripe normally means 5%. Silver, I think, would be 10%. Yeah, nearly caught me out. That one's 2K32, not 49.9. The 49.9 is over here. Just to catch out the unwary. And then we have another accurate resistor here, which is the 2.32K, 2K32. Which we should pop into the appropriate place there. So there's another 10K resistor over here. Oh, I don't see any empty resistor slots, so that looks like all the resistors are nicely ready to go. So just putting another circuit board to bear behind here, so I can put it upside down, slide it along the way, and they're all ready for soldering. Now my soldering iron has cooled down enough, at least with the pliers, just to change the bit back to my normal bit for soldering. So we'll just solder all these resistors in place now, using standard gauge solder. This one is 0.7 mil. Now, those who've seen my other videos will also know that for some reason this vertically USB sort of microscope camera makes the solder joints all look quite black. They don't look like that to the naked eye, so we don't have to worry too much about it. Swing it around to give me easier access to more of the pins. Visual inspection to see which ones I've missed. I can't see any that I've missed. If I have, I'll discover them as I snip them off. So with my small side cutters, which have become magnetic, unfortunately, which isn't ideal for this, but I seem to get away with it. So we'll just snip off all those pins that are soldered. So there's all those snipped off, so I can now do reasonably detailed visual inspection. Just to see that I'm happy with that, and that we haven't got any of the trimmed ends shorting against each other. So now I've got all those resistors and the diode in place, I'm going to transfer onto my PCB holder. So I can then put the rest of the components on. And I tend to do the pin headers next. So I've got a number of pins supplied. There are not as many jumpers on this one as there are on the CANEther. So I'm going to start with doing the programming header, which is a 6-pin. 1, 2, 3, 4, 5, 6. So I'll just snip that off. And when with the pliers, we just pull out one of the pins, which is the key pin. If I can get a grip. Here we go. Okay. In fact, I'm going to turn this the other way up, so it's the right way up, both for me and for you, living it and watching it. So it'll just make life a little bit easier. So my programming header is up here. So my technique, if you haven't seen it on my other videos, is that I just get my thumb behind onto one of the pins and solder a pin that I'm not holding. Just tack it on. And then I get my finger onto it. It sits all over the place at the moment, but I get my finger onto the plastic. Just reflow the joint and use the pressure of my finger just to set it. Double check it's all sitting nicely and straight. I can just, at my leisure, solder the other pins up. Now, this one doesn't have the jumper for which kind of CAN chip you're using. Because it's a 3.3 volt module, we have to use the CAN chip that has the split voltage capability to drive the CAN at 5 volts, and therefore there's no choice. We're using a 2562. And then we've got a couple of little connectors and jumpers down here. This one is to provide 5 volt supply if we wanted to power a pocket router from this device, save it having to have a separate supply. And then we've got JP1 over here, which I believe is for the sounder, the beeper, if my memory serves me correctly. So I've got a couple of 2-pins header. You can put a like a Molex type connector on there for polarity and so on. I'm just going to do this one as a simple pin header. And that's all actually all the pin headers on this one. So next I'm going to do the IC sockets. So here I have the bit of foam, which has the PIC and the Ethernet chip and the CAN chip and the various IC sockets. So I'm going to start, as I normally do, with a little CAN chip one. And this has the biked out of it at the end of the socket. And you'll see that, as with all or most C+ boards, it goes that way around, the other way up to most of them. So just got a bit of a hand on there. I'll just tap the 2 corners. And with a bit of firm pressure, just refurl the joints in case it needs to just go fully in. Quick visual check that it's sitting nice and straight and level and the right way around. And we'll solder the other pins. The one for the PIC, which is in the middle here. So for the same mechanism. You might choose to put the crystal in first, as you've got to get your finger in there to hold the crystal, but I reckon I can do it anyway. Just be careful you don't dislodge the surface mount chip there. These screws solder. That's looking quite nice and straight. I'm just going to push it down a little bit. Sometimes you feel a tiny bit of movement as you press it down and regulate the joints, just to make sure that's sitting nice and flat and straight. And we'll now solder up the remaining pins. Oh, I haven't put any music on this, but that was just too complicated to work out how to do that. I'm sure it's easy if one looks it up on Google. Some music background, but then I suppose you've got to worry about copyright and make sure the music you choose doesn't have that issue. Now the Ethernet chip is another likewise similar 40-pin device. When we come to put the chips in, we have to make sure we put the right one in the right one. Because those 2 capacitors are right tight between those, I am going to fit those first. Just be slightly easier than doing it afterwards. These are the 100 nanofarad standard decoupling capacitors we use with 104 written on them. Not really space to label those on the board, but since anything not labelled is going to be one of those, we're fairly safe. Just be careful to check the with the CANEther. You are putting the 104 nanofarad in there, because there are some one or two capacitors over on the far side which are labelled on the circuit board, which are of a different value. So you can't assume that any capacitor of about that size in the bag of bits is all the same value on this one. So now we can pop the other 40-pin socket in. Now those two are in. And just the usual technique, the two corners. A little bit of pressure to reflow those. Visual check. It's looking good. Now we'll next pop the crystal in. Now there's two crystals on this one, so you do have to make sure you don't get them mixed up because they are different values. One is 25 megahertz. You might just be able to read 25 on there with any luck. Reflects a bit with the camera, and that goes over to the right here. That's for the Ethernet chip, and then the pic on this one runs at 8 megahertz, and so there should be an 8 megahertz crystal. That one's got an 8 on it, 8.000. So that's the one to put over here, and it is important. It won't work if you get them back to front. So we'll pop that in. As with many other modules, there's 3 holes to allow for a resonator. And being at 8 megahertz, probably work all right with a resonator, but a crystal is generally recommended as the best choice. So I'll just solder those two on. Getting down nice and flush. And then we've got a couple of 18 nanofarads labeled 180. And they just go in here. Just next to the crystal as they help break the crystal. Now this is where you've got to be careful. That one C is labelled 270. So that's for use elsewhere. That's not the one I want. Here it is. Here's the right one, labelled 180. You can cross-check with the schematic if you want to be sure. But basically the 180 18 farad are for the crystal, and the other one you should find is actually labelled on the PCB, although quite small and not that easy to see. That's the right hand side. So while we're doing crystals, and I've got it in my hand, I'm going to fit the 25 megahertz crystal over here. That only has the 2 holes. That has to be a crystal, it can't be a resonator. The high frequency, I guess, and the accuracy required for the Ethernet. Because this one is to do with setting the timing on the Ethernet side. There we go. I didn't get that very straight, did I? So let's keep it down. Particularly a work fine like that. Let's just straighten that up a bit. Looking better. Yeah, you should just about be able to see. It's quite difficult to see, probably easier with the naked eye if you've got your magnification. There is a 27 PF labelled across there and across there. And so these will be labelled similar small ones. These will be labelled 270, which is these ones. I'm going to lay my fingers on it. And 270 again. Just have to splay the legs ever so slightly on this to fit into the board. Quite a few LEDs on the CANEther, so we'll get ahead and fit those. Now, these, the colour you use for the C-bus power and Ethernet, really up to you. I just described LD1, 2 and 3. We do have LD4G for the slim and LD5Y for the FLIM, the yellow. That is the normal convention for those. Since all my other boards are using red for power, I use red for power on here. And then C-bus activity, I guess I'm using green for that. Should, with any luck, have an orange one here, but I can't see it at the moment. Two greens and yellow. Red. I've got an extra yellow, so it looks as if we're using yellow here, not orange. That'll do. The colour doesn't really matter too much. It's just a flickering indication of activity. So let's move that down a bit so I've got clear access to the LEDs there. So next I'm going to move on to soldering the LEDs in. They're slightly fiddly and easier to do without all the other components around them. So I'm going to start with the slim and flim LEDs here, LD4G for green and LD5Y for yellow. As with the LEDs before, with a little plus sign here and a flat indicating the negative side there, so the longer lead of the LED will be going towards the positive sign. Reasonably straight by feel, check it's looking okay on the top, solder the other leg. You'll find the shorter leg, which is on the ground plane, may need just a little bit more time with the soldering iron to get the solder to flow properly. 3 more LEDs here. So I'm going to use an orange LED for the Ethernet. It's just an activity light, so again plus sign to the longer leg. Needing a little longer with the iron on the negative pins of the LEDs, which are on the generally but not always on the ground plane. Then we've got the power, so I'm going to use the red LED for that. So that's our normal convention for power on C-bus modules. And for the C-bus activity, I'm going to use a green LED. It's quite normal for green to be flickering for C-bus activity, generally on C-bus, so that seems a good enough convention. But feel free to put in whatever colour you like. That's all the LEDs fitted and ready for action. So we'll just put the little decoupler. Now careful with this one with capacitors, because there are different valued capacitors floating around in different places occasionally. So the 104s are the little decoupling capacitors, so if it's not otherwise labelled and isn't shown on the PCB as polarised, it's going to be 100 nanofarads. You can of course cross check against the schematic if you're unsure in any particular instance. We've put a couple of them in here already. And there should be one over on the left here near to the CAN chip, and indeed there is one just there. So I'm going to pop that one in. By the way, you've got an extra LED down here, diag, for diagnostics. The firmware doesn't do anything with that at the moment, so you can fit that or not as you wish. I've got a spare yellow LED floating about here, so I'm going to fit that in that place, just so that as and when I do get around to putting some diagnostics in the firmware, so it can tell you something's wrong or whatever, then I've got an LED in the space. Which serves as a reminder to me I ought to do something with that. Maybe something about when it gets its IP address or something. Might be an interesting thing to do. And there's another capacitor over here, C9, which is also a decoupler. See if there's any more of those. C13 looks like it's one of those also. So another 104 there, and we'll pop that in too. Okay, let's put the little switch in, which is here, the flim switch, which is also used on the CANEther. If you power it up with the switch held down for just the right amount of time, it'll switch between using a static internet address, IP address, and an address that it gets from your router or whatever's plugged into your network to provide addresses. It can also be used to put it into flim, give it a node number as you would with any other CBus module, and you can then change various settings using the FCU program. Okay, we've got some more capacitors. There's a 10 microfarad capacitor here. In actual fact, the 10 microfarad capacitor is, strictly speaking, not needed because of the type of processor we're using at the moment, which is a large memory version of the original PIC18F series. But the 10 microfarad capacitor is there just in case we do decide to use the K series at any stage. I guess it's more likely now that if we were upgrading the processor we might go straight to the Q series, which no longer requires the capacitor, but generally speaking it doesn't do any harm to have it in there, so I'm going to fit it. And then there'll be a few 4.7s scattered around doing their decoupling work on the different power supplies, because we've got both the main 3.3 volt power supply to work the Ethernet and the PIC, and then there's a separate 5 volt supply onto the CAN, and the CAN chip actually has a split supply for that purpose. So there will be these capacitors on both supplies. You can see a longer leg and a shorter leg. These are polarized capacitors as indicated by the shape of the outline there. You can see it's chamfered at one end and there's a little plus sign, and if you can read it, just in there it actually says 4.7, so it is labelled for you just to make sure the right one's going in the right place. Is me trying to do the one on the ground plane and having to hold the soldering iron a little bit longer to get the solder hot enough to flow. And you can see when the solder flows as you're soldering, once you get a feel for that. So we've got another 4.7 up here. Get that one the right way around as well. If you get one of these tantalum capacitors the wrong way around, when you power it up you'll hear a little noise and there'll be a bit of smoke, and you'll have to change that capacitor. How do I know that? Been there, done that. Another 4.7 down the back here. and one more over here. Likewise, that's a 4.7. That goes in. Now, there's two voltage regulators here laid out, and there's an interesting point here. So you've got the 3.3 volt regulator there, and we standardise on a switching regulator for these. You generally only have one on the layout, so they are a little bit more expensive than a standard 7805. And if you can see that, it actually says 7803 on that one, -500. That's a 3.3 volt version, and that goes there, and that's providing power for the main PIC and Ethernet chip. Then we need 5 volts as the split supply into the CAN chip, because you need 5 volts to get sufficient voltage on the CAN bus. And it's laid out to take a little 78L05 regulator, which is quite sufficient for the power for just the 5 volts onto the CAN bus. However, it's also laid out to take the bigger switching version of the regulator, and the reason for that, and that's an option when you're building the CANEther, is that the 5 volts is also available on this pin header down here, and the little pocket routers we use with these, if we're going to put it onto Wi-Fi, actually will run off 5 volt supply. So instead of having to have a separate supply for the pocket router, you can power it from the CANEther here. Now that obviously is taking a bit more current, and therefore the little tiny regulator wouldn't be sufficient, so you fit the bigger switch mode regulator. And because this one may well be used with a pocket router, I'm going to fit the switch mode regulator. So that's an option. If you buy your bag of bits kit from RME, you can actually select in the drop down when you order it whether you want the switch mode regulator for the second one. Be careful you fit them the right way around. The only difference is the one that says 05 and one says 03 on it. Other than that, they may well look identical. And the PCB is laid out 5 volt, 3.3 volt, so you can see clearly enough. So I'm putting this one into the 5 volt position. There we go. And again, I'll just tack one pin initially. The middle one is the ground pin, so therefore slightly more difficult to do. And then, as you can see, with one pin tacked, it's not very straight, so I will now just reflow that. See if I can get it fully nicely pressed down. And looking a bit straighter. Not quite perfect yet. I'm going to be finicky about this one. We'll just see if we can get that dead straight. I'm not doing very well here, am I? My board's coming slightly adrift in the holder, so we'll just tidy that up a bit and we'll have another go. Of course it would work fine if it wasn't dead straight, but I like it to look nice if possible. How many goes is this going to take? We'll have a go at soldering the pin at the other end, and then hopefully that will sit straight. think I'll tick that box now. I'm happy that that's straight enough. So we'll solder up the middle pin. So now we have the 3.3 volt one. You'll notice that on these regulators, the pins are offset to one side, and likewise on the PCB you can see they're offset to one side, so quite difficult to put it the wrong way around, because if I did, well, they wouldn't both fit, but also it wouldn't be within the outline shown on the PCB, so it is important that they do go the right way around. So likewise as with the last one, I'm just going to tack one pin. And put some pressure on it and see if we can get it reasonably straight. Yeah, that one's come out quite nicely straight away. So we'll get the other two pins soldered up. There we go. That's the two voltage regulators fitted. And we've got a capacitor on the input as a reservoir. Just there. This is an electrolytic. Again, you've got a plus sign on the board there, and just about see that the negative side of the capacitor symbol is filled in with the white there, and the capacitor itself has a longer leg for positive and these big dashes for the negative side on the side, so no excuse for getting it the wrong way around. If you do and you power it up, these ones will actually go bang rather than fizzle compared to the little tantalums. So quite a lot of smoke. And then you have to fit a replacement. You generally won't damage anything else. So I've got that one tacked, not very straight yet. Put some pressure, reflow the joint, get it nice and straight. And solder the second pin. That's looking nice enough. And the first pin just needs a little bit more solder. Tacked in the first place. There we go. So I'm going to fit the C-bus connector now onto the end here. We'll tack one pin. So we can now just solder up the other pins. Next, this is a little inductor. Now, reports are that actually if you don't bother to fit the inductor, it actually still works fine, and just put a wire link here instead. But if you buy the bag of bits kits, it comes with the inductor. It means it fully meets the Ethernet spec. It should be in there. It does have one leg longer than the other, so there is a kind of polarity, but in this application the polarity doesn't actually matter, so you can put it in either way around, no problem. So I'm going to tack one side again, just as I usually do. Push it in nice and firmly whilst reflowing the joint. That's not exactly straight, so we'll reflow that again. I think the base of these isn't dead flat, so you kind of got to judge it by looking at the pin there as you resolder it, and now that's looking a lot nicer. And finally, we have the Ethernet connector. Now this isn't just a socket. It's got magnetics in it, so it's an inductive coupling into the circuit. All of the right impedances and everything, plus it's got those two LEDs which will flicker to give you Ethernet activity when it's on. It's got multiple earthed pins for holding it in, and then the LEDs actually driven off these pins here, and the main Ethernet interface is from these pins here. So we'll drop that in and be careful everything's lining up. It has these quite chunky plastic pins here which give it a good firm seating, but they need a good firm push in. But before you give it that good firm push, you make sure that your pins are actually lined up. You'll notice one of these pins is not connected on this. That's because that pin isn't used. So it's not it doesn't mean your socket is actually in any way faulty. So that's gone in nice and firmly. So what I will do first is I'm going to solder up these two holding lugs. We'll do one of them first, and then make sure it's sitting nice and straight, push it down, and then do the other one and repeat that exercise. Needs a fair bit of time and solder on there because there's quite a lot of metal attached to that on the socket, as well as the fact that it's on the ground plane on the board, so a lot of earthing going on there. That looks okay. So sitting down nice and flat, I'm going to give it a little bit of pressure from below and just reflow the joint just to make sure it's fully in, fully home. And then we'll do the other pin likewise. And you don't want to be melting the plastic leg with your soldering iron either, so I've got it on the pad and on the pin for a fair while to get that solder to start flowing, and hold it on for a moment after to make sure that's flown and done a nice joint for you. So we can see that's sitting nice and straight and flush with the board, and then we can solder up all the other pins. So we've got the ones at the front here, two that actually drive each of those little built-in LEDs, and then the actual data connections down here. I'm going to do the left ones first, as that's slightly more fiddly to get the soldering iron to. That one, of course, looks slightly different because there is no pin in it, so I needn't have soldered that one. Not that it does any harm, of course. Right. So at this point, quick look underneath. Are there any pads that haven't been populated? As always, yes, one or two. You've got the one in the middle of the crystal there that would be if we used a resonator on the pick, so we know that's correctly not used. So these are the three pins that, had we used the smaller regulator for the 5 volts, because we've used the big switch mode, they don't get used. And all the other pins on the board are populated. So I'm now going to pop this out of the thing, have a quick visual inspection, and we're going to snip off all those lugs now. Generally point the board away from your face as you, just in case anything flies off. They don't usually, particularly with my annoyingly magnetised cutters. I think that happened in the toolbox, so I have to keep pulling the bits off it. But you can, like the sort of action which becomes instinctive is that you put the cutter on it and then you just tilt it away from your face as you clip. So the PCB is acting as a little sort of protector if anything does fly off as you snip them off. They usually don't, but they can. And as you see, my preference is to solder all the components and then snip them off. Unless it gets too crowded to get the soldering iron in, then I may stop and snip some off part way through, but it's just quicker overall to do all the snipping at the end in one go. I'm going to have a look there and see if there's anything sitting excessively proud, but that's looking reasonable. Make sure I haven't got any little bent wires which might be shorting out anything. Visual inspection. One little wire there that I've missed which potentially could bend over and catch something, so we'll just snip that off. And then time to give it a clean and make the soldering look nicer. Spray of the solvent, trusty toothbrush. I wouldn't use it for cleaning your teeth after you've used it for this. And that does actually make your flatter your soldering when you clean it, because it makes it look a lot nicer. So we're ready now for the static voltage checks. So I will take my C-bus cable, which is attached to the layout, and we'll just plug that in and see if anything goes bang. First good thing to check, particularly when, like I've been doing, you've been cutting off these little things, be good not to have it sitting on any of those, because they might well short pads and undo all your good work. So make sure you've got a nice clear surface that you're putting it on there. It's not going to short anything. Okay, so we have, although it looks a bit orange in the camera, that is a red light, which is indicating power. And that will be on the 3.3 volt supply, as that's the main supply. So I'm going to get my meter now and we'll do some static voltage checks. We'll see how it goes. So we're going to put the going to test the incoming supply, and it always helps. This meter has this annoying habit of, when you, even if you were measuring DC last time, is when you turn it back on it comes on AC, hence I'm not getting a very sensible reading. So now we'll try DC, put it on the input reading, and we got 11.9 there, so that's near as no, it makes no matter the 12 volts incoming C-bus supply. Now if you take the two middle pins away from the C-bus connector here, we should see our 5 volt supply for the CAN bus, 4.96, as you can see there. And then what I can do is, if I take pins 8 and 20 of the pick, and the pick is the leftmost of these two devices here, 1, 2, 3, 4, 5, 6, 7, 8 and 20, and we've got 3.3 volts, which is what we should be seeing. Now if you want, you can do additional checks onto the second, find out where from the schematic what the power pins are on the Ethernet chip here, but I'm happy, having built a few of these, that if I've got the right power supply on this chip, I'm going to have the right power supply on this chip, and also that the 3.3 volts will be on the appropriate chips for the split power for the CAN chip. So I'm happy with that. So now I'm going to unplug the power. I'm going to put on my anti-static strap for handling the chips, which is always important, particularly with the CAN chip. And here are the 3 chips that are supplied with the kit. So I'm going to start with the CAN chip. Now the CAN chip, a little bite out of the chip is towards this end, and this chip is the other way up to the others. The little bite, if you fitted the socket correctly, will be down that end. And what I do is I just put a little bit of sideways pressure on the legs just to bring them in, and that's popped that one in. Now these two are the same size, but they're not the same chip, so you do need to get them right. So which you can check with the schematic if you wish. IC2, IC3. IC2 is the pick, so we'll put the pick first into IC2. Now if you bought this as a bag of bits kit from RME, it will be pre-programmed with the CANEther firmware. If you've just bought your own chip, you will need to program that using a PIC programmer. So again, I'll just put a little bit of sideways pressure to just ease the legs in. This is my technique. You may well have your own technique for doing this. You can buy special tools for it. And just gently side to side, putting a little bit of pressure on, not too much, otherwise you'll bend the pins and it will go all at once. There we go. Got that lined up now. Quick visual that all the pins are lined up correctly, none of them are bent. Just going to ease it towards the top slightly as they're not quite in the middle of their sockets. That's better. And push it in. And we'll do exactly the same with the Ethernet chip now. Again, making sure that the bite here corresponds to the top, and a double check that I've got them the right way around. There it goes. So now we have it with all the chips in, so we can power it up again. And you'll see we've got a green light for Slim, that indicates it's running. The power light's on. The Ethernet stays on for a while it's looking to see if it can get an address from anywhere, and goes out when it's completed that process, which will basically be, in this case, well, it's not getting one from anywhere else, so it'll use its own. The diagnostic leg just sits on, that's not doing anything at the moment. And that's ready to try out, so we can actually give it a go. And there'll be another video to come in terms of connecting, setting up, configuring and using your CANEther. Thanks for watching.